Welcome to our class. Today we want to look at structs and arrays in NoirLang. We've seen how to, in our previous lessons, how to come up with the circuits in Noir. So this is just a continuation of what we've been doing. We're trying this time to incorporate structs and arrays. So we'll see where this is possible and where it's not possible in our today's lesson. And as we look at examples, now it's not always that we'll be using structs and arrays as we write, but there are areas where we can use structs and arrays, and there are areas where we cannot use because Noah is still evolving. So it has not been fully incorporated. It is a good thing. So that's why we are looking at it today. So we'll see how to declare inputs. But before that, we just do some recap of what we've covered so far in our previous lessons. Just take you through what we've been covering. And then after that, we look at our lesson today, which is about structs and arrays. Now, previously we saw how to declare inputs as either being public or private whenever we are writing our circuits. So for instance, you can see I've used the word pub here. And the word pub, as we've always seen, is used to if an input is public or even an output. An output or input which is public will be indicated by pub. Now, if you don't indicate by pub, it's then assumed that that input is private. So that's how I've said in Noah, variables declared with pub are visible to the verifier. So the prover has put pub, that means the verifier can see what that value is. So if the value is 17, this 17 is visible to both the prover and the verifier if it has pub indicated. But if it has no pub, it means this is a private value, and therefore only the prover knows it, the verifier does not. So I've said why this is important, and again, this is just a recap. We say that this is essential for ZK proofs, where public inputs usually are part of the statement being proven. Usually, public inputs are part of that statement. So this is just an example of how you declare inputs. So if pub is not indicated, it means that input is private. Now, usually we add constraints by use of the word assert, and we've seen that in our previous examples. The assert keyword enforces logical conditions. That is, it enforces the constraints. Now, this will help either the condition to fail or to not to fail. So if the condition fails, the proof will not be generated. If the condition inside the assert, where you are asserting, if it fails, then the proof is not generated. But if it passes, then the proof is generated. Now, the other thing that I need to just again repeat, and we've already looked at, is proving and verifying using BB command. And this is what we've been doing. We said that Nago does not have the command Nago prove, Nago verify, and so on. And so, okay, it has Nago compile, Nago execute, Nago test, but prove and verify are not there. So we then use BB commands, which is from Barentenberg. And we've been using this before. We've used it before. And so this is just a recap, as we've said. So we have Nago compile. Nago compile, this compiles Noah code into circuit artifacts. Nago prove, no, BB prove. We don't have Nago prove. So BB prove, and I'll remind you the code. I'll remind the code in the next page. But what this one does, it generates a zero knowledge proof from the compiled artifacts. And then verify, BB verify, checks the proof's correctness against the public inputs. So this just a repeat of what we've done so that we are familiar with it before we proceed to the structs and so on. Now, so the commands for the proofs we've seen before are this. To generate the proof, and you're using BB proof. And in our previous lesson, we said we would make a directory in the target, and this directory should be called proof directory. So this is where now we shall have the proof folder with the proof inside. But now the command is this, BB proof. So I put these two. You can use one. You can either decide to use the ultrahonk, or you can decide to use the Oracle hash kekak. So you decide on what you want to use. And under you're using, then you be consistent, use it consistently, even to the verification of the proof and so on, a key generation and so on. So if you're using this, then be consistent down as you proceed with the verify and so on. And if you're using this, also be consistent and use it in the rest of the commands. So for me, what I'll do, in the rest of the commands, I'll stick to this kekak. So I'll not be working with this. But in our previous lessons, we've seen how to work with both of them. And of course, again, I still emphasize at that point that you need to be consistent. Once you choose one, move with it to the end. Now, so this will be the name of the project. And of course, this one you can always see it in the Nago domain, nago.toml. So the name of the project, which is always in the Nago domain. So this is what you put there. And again, it's the same thing here, the name of the project. And then the proof will be stored inside the target in the folder called proof directory. And this is what we formed here, that directory is what we formed there. So again, these are commands we'll be using just in a short while when we'll be doing our hands-on work. Because once we learn about structs, we will then try to do it practically and to use these proofs. And of course, in our last lesson, we saw how we're writing these proofs in the build.sh or run.sh, those scripts, how we are writing it in the scripts to automate our proof generation, key generation, and so on. So again, these are the same commands you can put in those scripts to automate that this process of proof generation. Now to generate verification key, and I said I'll be using kekak, so so you can see that is what I'm using, Oracle hash kekak. So I dropped the other one. But if you wanted the other one, then you would just replace this by that. So write BB, write verification key, And then that verification key should be stored inside target, and it should be called, this is the name of the project. For this example, I've used edge verification.json. So it will be stored like that. So the verification key is derived from the circuit definition. It is required to verify any proof later. So if you want to verify the proof, you'll require the verification key. That is what it does. That is its role, just to assist verify the proof later. Now we are at the point of now verifying that, that proof. And again, I've stuck on Kekak. I said once you choose one, you stick to it to the end. So BB verify. So you're going inside the target, and there's this VK, the verification key. Then there's a proof. So this is the proof we want to verify. This proof is inside the proof directory, which is inside the target. So this uses VK and proof to validate the correctness of the proof. That's the explanation. So that's what this code does. This code uses the VK, the verification key generated above. The verification key generated above. We generated verification key above. Here, this is where we generated it. We wrote VK at this point, verification key. So after writing that verification key, the command we've just looked at, this command, this one, now what it does, it will now be using that VK and the proof that was generated earlier to just validate its correctness. This step simulates how a verifier, contract, or application would accept a proof. Now, so we now want to generate the verifier, the solidity verifier. Solidity verifier will just use this, and it will be sent to the to be now contract called verifier.sol. This is where the contract is. This is our contract, the verifier, and this is how we generate it. So this was the recap of what we've done before we proceed to the structs. Now, just some explanation on this generate solidity verifier. The thing is that it outputs a ready to deploy solidity verifier. So you can deploy that one directly. Now, it's useful for on-chain ZK verification in Ethereum compatible environments. Now, the other thing I just want to mention is when you're writing a circuit, now this is now the introductory to our structs and arrays. Before you do that, we need to recall what we normally do when you're writing the main and the circuit inputs. All Noir programs define the main function, which serves as the entry point. Inputs to this function represent the values involved in the proof logic. So we've seen how to write the main function, and of course we will recap that. But now, before we go into the main again, what is this thing called strut? What are struts? So then I define what the struts are, and then show you how to write struts and how do we connect it to it there. with the main function. And then from there, we do our practical lesson. So a struct is a way to group related fields into one logical unit. Related fields. Now, what does it do in Noir? We use structs in Noir 1 to keep code clean and organized. 2, to pass multiple values into functions as a single object. So where you have multiple values and you want them inside a function as a single object, you will use structs. So structs will put them together. Then reuse types in different parts of the circuit. Now, these functions will become clear as we look at examples, but that is what structs will then be doing in our circuits. That's what they'll be doing. An example of strut is this, is strut person. Then we have age, which is public, and then there is verified, bool. And again, this one is public. Now, so this strut will be put at the top of the main function. So you have the main function, which you've written, then you put the strut above it. Strut is just put above it. So this defines a new type called person. It has 2 public fields, age and is verified. Is verified. Age. These are public functions. You said if they're public, then you indicate by the use of the word pub. So therefore, pub, a keyword means the values will be visible to the verifier, as I had already mentioned. So the fields use valid Noir types. Field are just numbers. And bool will be either true or false. Now, I've already said this point that if you want to use strut, then you must declare it before the main function. You declare it before the main function, not the other way around, not the main function and then the strut. It is the strut first, then main function follows. This is just an example. And this example is where now it has been done reverse. I've declared the main function, then I've declared the strut, and I've said this is an incorrect way of declaring strut. You don't declare main function, then you declare the struts. That will be incorrect. So the correct way of declaring it is the strut first, and then the main function. Now, this is just an example, but we'll look at, we'll do an example and see how it works. Part of an example that we've looked at before without using strut, and today we'll now be using strut. Now, this we've seen before. We've seen this main function. We've seen it before. We've done it where we are where somebody wants to prove that he's between 18 and 60 years, without necessarily having to tell us the exact age. So the person is telling us that it's between this range. It's between the range of 18 and 60. 18 could be included, but this guy does not want us to know what the exact age is. Look what they assert. So if the is greater or equal to the minimum age, or if the age of the person, P, because we declared the strut here, person, and then public, age is public, and is U32, and we not just say that this person will be referred to as P, and so that P is what we're using here. So if the age of this person is greater than or equal to the minimum age, let me see, the minimum age is 18. Or if the age of this person is less than or equal to the maximum age is 60. So just asserting. Now, so if we run this code, it will accept if the age is within the range. If the age is within the range of 18 and 60. But if the age is too young, if the person is too young, that means the person is below 18 years. It will not compile. And if the person is older than 60 years, again, will receive errors. It will receive errors for that. But remember at the end of the thing that these things are possible zero knowledge proof. That means the prover, as he does whatever he does, whatever age he inserts, the verifier will not be able to see that age. The verifier can only see if it compiles, if it runs successfully, the verifier will just see that this guy is within the range of the ages given, it's within the range of 18 and 60, if it compiles successfully. Now, if it does not compile successfully, it means this guy will be either younger than the 18 or the guy is older than 60. But at the end of it, the verifier will not know what age the guy is. So, but the point is, we've already looked at this circuit. The point is, what we wanted to see is how do we write strut for this? I've written here struct, person, pub, age. So you can just copy this, code and paste it inside your main.nr, and then begin nago compile, do give it. You can now, if you want to do nago, nago execute, you would give it the prover.toml first. And if you want to do nago test, you would add some tests as we've always been doing, in our previous lessons. So you can do nago execute. And if you do nago execute, yes, expect to receive this output if it compiled correctly. But before you do nago execute, give it this in the prover.toml. In the prover.toml, you give it this. Okay, so I think that at this point we need to do it. We need to do it practically. So just I'll be sharing my WSL to just begin the process of writing the code. I'm just preparing, looking for where it is. Okay, WSL. So I want to share my WSL. Let me share this. We try and create this so you see how it works. Of course, you know how to what we've been doing, and so the first thing I want to go into where I store my programs and just say CD Rust programs, because that is where I store my programs. Now, so I want to create a project and I want to call it just give it any name. There's no problem. Can call it, we've already used age range. So I think I can call it another lesson, and just call it another lesson. So I say make directory, and I'll call it another lesson. Let me get inside this. Good. Now, once you're there, you want to say Nago initialize. Okay. Mine says that because of the path, I'm not in the right path. My Nago is not well installed. And so what I do, I want to give it a command that will take it to the right path. And then I repeat the same thing. I repeat the same command. But first of all, I must have it in the right path, because that is what you're seeing there. What you're seeing is that it's not in the right path. Later on, I may need to uninstall it, and then install it properly later on, because it's telling me cargo Nago not found. Did you mean cargo and so on. So that just means that is not in the right path. That's what it means. It does not mean that I did not install it. I already installed it, but so for me, just to ensure that in the right path, I can come out of this project we just created, give it this command. And this command ensures that it goes the right path. And so once in the right path, I can come back here and CD that, just repeating the same process. And this time it has accepted. So let me just say Nago initialize. And this is what I was doing when it rejected. Oh, I did not write it properly. Is it? I did not write it properly. Do I write? Yeah, I did not write it properly. It's supposed to be Nago. It's I-N-I-T. I initialize, not what I wrote. Good. So the project has been created. It's located here. So I can now open this project, cargo, no, code, space, then dot. And then when I click enter, it's supposed to open for me a visual code. And that's what it's doing from my end. So I can close this. I can unshare that and then share the VS code that is open on my end. Let me enlarge it first before sharing. Enlarge it. And then share it. So when we did Nago initialize, there is Nago here opened with the name of the project as another lesson. But just above it, we have SRC with the main.nr, and this is the default main.nr that comes with it when you open. But we wanted to change this to hours. Wanted to change this to hours, which I had shared in my slides. So I just want to copy it and paste. And then we try simple things like Nago compile to see what happens when you do Nago compile. So what I do, I just delete what we have and replace it by my main. My main is here, my main function. And just above it, we have the strut. Just as I had explained in the notes, strut person. Then I've defined the person to be P and so on. So we can run this. This is my terminal. We can run, but just before that, note that we don't have targets. But when I run Nago compile, we get that target. Nago compile is what brings it. So I'm writing that in my terminal, enter. And you can see you have target here. It's now, it has come, and it has another lesson.json, and that has this is what is inside. Now, so we cannot say Nago execute at this point until we add the provers prover.toml, until we add that. But before then, it will not compile. We can try. Let's just try and see what happens. Let's say Nago execute, and see what we get. It has said error, cannot find prover.toml file. Expected location of that is home, Cyprian, Rust programs, another. So in the root project is where we are supposed to do that. I just click here and new, press new, then write prover.toml, because it has told us that it expects it in the root. When I press enter, it gives me a place to write this. I've put an age that is expected to be correct between 18 and 60. Now I can try and say Nago execute and see what comes out. Now it has worked. It has worked, and it's saying another lesson: circuit witness successfully solved, because Nago execute gives us witness. So it says the witness successfully solved. Then it says this witness has been saved as another lesson.gz inside target. It has been saved inside target as another lesson.gz. So when you just come here, this target, you can see it is here. Another lesson. So this is the witness. But this one was formed before. This one was formed when you did Nago compile. But when you've done Nago execute, this has formed. This is what has come about as a result of that, the witness. Good. You may want to do tests. You may want to do Nago test. And so if you want to do Nago test, it means, as we've done before, you may want to write tests. And again, just remind you how we've been writing tests. Begin by hash test inside these brackets. Then you are testing the main function. You're testing the main function. You're testing whether the edge is valid. So what edge? You want to test 30. If 30 is valid, let me just open another terminal so that we work. I don't want to see anything red. So now you can say Nago test, because you have some test there. It can now, good. There was only one test and it's successful. You remember, if I remove this test and do Nago test, there'll be nothing to test. Let's see. Nago test. I've removed the test. It says, it compared, but it says running. There was 0 test passed and there was 0 test functions. Can you see this is different from the first one? The first one says it was running 1 test function and then 1 test passed. So this time it ran, but of course there was no test. So there was 0 test function and so on. Now, so if this edge goes below 18, if it goes below 18, let's again do Nago test. Nago test. The edge is below 18. it has failed. So it says it ran one test, testing the valid age. So the age is not valid because we have this assert. Now we have the assert here. The assert here. So if it fails, then if it's not within the given range, then it has to fail. So it says error assertion failed. Too young. It's too young. The guy is too young. Is not in the bracket that we were given. Even if you are to try and raise it, let's put it at 70 and do NAGO test. This one again fails. What does it tell us? The guy is too old. It's too old, and the maximum age. Maximum age is supposed to be 60, so this guy is beyond that. Let me take it back to 30, where it was. Now let me come to this prover Tomil and put 15 here. Prover Tomil, put 15 and say NAGO execute, NAGO test. NAGO test. Now, so what has it passed because of our test. Our test has 30, so it passed. So this one has no impact on what you had. Let's try and, but this time put something bigger and say NAGO test. Again, it passes. So this one, the NAGO approval TOML is just required, not for the test, but for the execute. When you remove it, the execute, which generates the witness, will not work. The execute which generates the witness will not work. But it will not affect the test. What affects the test is the edge you inserted inside the test is what affects it. Okay, so, but the point was the struct has been used at this point. Now, it does not mean that when I remove it, this will not work. But now, when I remove it, it means, again, the way I write this would have to change. The way I write it will have to change because of that. Now, we'll come back to this code and explain a few things. For instance, okay, running the proof, that one has no problem because we've done it before. Generating the proof and so on has no problem. We can try and generate, just let's try and generate the proof for the sake of completeness, so that our notes are complete. And again, just so that we can also recall, I'll be using the same code I had shared in my notes. And the code is this. This is the code. Make directory called proof directory db. So the only thing I'll be changing is the name of our project. The name of our project is another lesson. So that is the only thing I'll be changing at this point, because our target that has another lesson. Our target has this. When we did Nago compile. This is what our target got. And when we did Nago execute, this is what our target got. So you can see without Nago execute, you do not have this witness. And so you cannot generate a proof without a witness. That's why we require Nago execute. Now, so with this, we can generate a proof and we expect it to go to the target, and we expect a directory called proof directory. Let me just press enter. You can see already we have proof directory here, and inside we have the proof. Inside we have the proof, although you cannot see it. But if you do cut, you can be able to see it. If you do cut, we had already talked about that. Now, we can also generate verification key just for the sake of completeness, that our notes are complete. Okay, so generate the proof. I want to generate verification key. And again, I'll be using this code. I only need to change the name of our project, which is another lesson. So I just change at this point and write another lesson and copy the whole thing as it is, come and paste it in the terminal, and you can see verification key has been formed inside our target, and it's called VK. So that's what we said. We said BB write VK inside the target, and we'll be using another lesson.json, which is already inside the target. We already have that. And you also be, of course, we said we're using this. Now, so it has finalized and it tells us VK has been saved in the target as VK. So that is the verification key. Now you can want to verify the proof. You can want to verify the proof. And if you want to verify the proof, the code I'll be using to do that is, I'd already shared this code that is here. This is the code I'll be using to verify the proof. There's nothing to change here. Just copy it the way it is and paste. It says verify the proof in the directory, and of course you're using the verification key. And it says the proof verified successfully. If the proof will be wrong, then it will have failed. It will have failed. It will not have been verified successfully. Now, after that, you want to generate solidity verifier, of course, our contract. And so, again, the link to that is this. I had already shared, and there's nothing to change. It's just the way it is. You copy it, and you want to see verifier.sol formed. So yes, you can see verifier.sol is here. So when you click on it, you see the contract. You can scroll down, and see what type of contract it is. You scroll down, you can see the contract. Hong verifier is base Hong verifier. N log, N number of public inputs, and so on. So this is the contract. Now, so that is how you do that. That's how you do that. So And let's continue with our PDF. Just to explain a few concepts, and then I give another example, then I leave you, you'll try the rest later. Now, at this point, we had talked about the strut coming before the main function, and why that matters. Of course, I've shown how it matters. I've said this is invalid, incorrect, and this is correct. And so we looked at this example. This is the example I've been explaining, and we've done it hands-on. So at your own time, you can try it again and see that it works from your side also. Now, so what if we are dealing with the several people? Can we have strut and array? That is the question. And remember, when we began my lecture, I said there are cases when you cannot use strut, there are cases when you can use it. So what is our goal this time? We are dealing with the various ages. Our goal is to validate multiple people's ages using NOIR with each age input separately. So that is our. Now, so this time I'll not use a strut. This is how I'll write it. I want to look at three people's ages. And so my main function would be this. This would be my main function. To get the assert, so I'll be doing assert for each person. You don't do it just once, like once for all people. You do for each person. So I've worked with 3. You can work with 4, 5, 10, 20, and so on. So the main function will have age for person 1. And of course, this is private. You can see. We don't need to see the age of this guy. It's a private thing. So we've not added pub. And age for person 2, age for person 3, and all these ages are U32. So let the minimum age be 18 and the maximum age be 60. Now you assert for person 1. If the age of this person is less than the minimum age, if it's less than the minimum age, and if the age of this person is greater than the maximum age, that is what we are talking about then. Then the person 1 age out of range. So if the age of this person is less than the minimum or is maximum or is greater than the maximum, then it's out of range. The same thing we assert for person 2. If age is less than the minimum age or the age is greater than maximum age, then the age of this person 2 will also be outside range. And so on. And even for person 3. And if you want, we can also now, after this, you can add tests. Now, this time, we've not used strut for this example. Now, so the explanation to the code is each person's age is passed as a separate U32 input. We define a valid age if it's within the range between 18 and 60. Constraints are applied individually to each age. So each age one age might fail, the other one might pass. But then that means the test will have failed. If one passes, another one fails. So we shall see that example. I've used this and not this. Because Noah does not support this. Noah only supports this. So when I'm declaring this, I was careful to use this. We'll try and see when you're writing this circuit. We'll try to use a double end and see whether it will work. Now, why this works is that Noah supports multiple scalar inputs like U32. So that is when I'm referring to the edge. It supports the edge of person 1, person 2, person 3, person. All of them put as ones. Node support. All constraints compile down to circuit constraints that can be proven. Noah currently does not support arrays of structs, e.g. person, several people. Like in this case, I was talking about 3 people. So Noah will not support arrays of structs of persons. So if there are several people, Noah will not support structs. So attempting to loop over 3 people or 4 people or 5 people will not work. But other languages would do that using I people. So where I is the number of people, could be 5, could be 10, could be 3, and so on. You could loop over arrays. So Noah does not yet have full ABI support to flatten and serialize struct arrays properly. So remember, it's still a growing language. It's still developing, so it does not have this inbuilt, but maybe in future it could be there. Now, so the circuit we just did above, its proof atomil will be this. This will be its proof atomil. Okay, so I think at this point we can try hands-on. But before that, just finish writing tests. We've already seen how to write tests. And why do you write tests? And the reason is, one, tests will let you check logic before generating full proof. So they provide quick feedback on circuit behavior. So that is why we need those tests before we proceed to proof generation. And this is how we write tests. You have to begin by this, then this bracket inside the word test. And then after that, you test the main function. So it's the main function that you're testing. Now, so this time, let us make a circuit. Of course, I'll not begin with the make directory. I'll just begin with what we were working on. And what we will do is we will delete the main, the code in the main, and replace it by this new one. And then also delete let me delete target permanently, target. And then this prove as toml, let me again remove it. Of course, we can just change it. Since we know how to do why we require the prover toml and so on, let me just maintain it. So we want to replace this code by the code for the next example, the one that involves multiple people. So we can work with 3 people, we can work with 4 people, and so on. You can generalize it later to several people at your own time. But we said this one will not be using structs because Noir has not yet reached that stage where it uses that. So this is our main. So I deleted target because it will have given us a wrong, it had already a witness which was wrong. So let's now compile this, Nago compile to generate new witness. Nago compile. Okay, now our target is here with the new witness. You can see our witness here is different from the one we had earlier. Very different. Very different. Now let me try Nago execute with what we have and see what we get. Nago execute. Just trying it with what we have. It has said it expects argument age P1. Now P1 underscore age. Let's look at what our main.nr says. Yes, says age P1 underscore age. That's what it's expecting. It's also expecting P2, P3. But what do we have? What we have is P. So what is it? It's expecting something else. And what we have is different. So that means you must give it the correct age. So it's expecting the age for the first person, then the age for the second person. And so this is what it's expecting. It's expecting this. The age for the first person, age for the second person, and so on. So let's now do Nago execute at this point so that we can get our another.gz, another lesson.gz. Good. So it has accepted, and now we have another lesson.gz. This is our witness. So that is what it does. Nago execute generates a witness. Now, so if you want to include tests, we can do that. Include tests. I want to include one that is bound to fail and one that is bound to pass. So we do that in the main.nr. So the first test, the age, the first person is 20, the second person is 30, and the third person is 50. So this one is supposed to pass because these guys, all of their ages are within the range, the required range. But the one that I've muted here, these ones are bound to fail. This one is bound to fail, so I'm not running it. That is why I put this backslash, so it will not compile. I'm not running it. The reason is this guy is 13. Although these two are within the range, this one is not within the range. So let's say Nago test. Okay, so there was one test and then it passed. Now let's now include this. Let's now include this and just remove this and then run it. Let's now again do Nago test. Okay, it fails. What does it say? What does it say on failing? What is that? Let me go to where it failed. It says, cannot find this in the scope. What is that? Okay. This should fail due to person one being underage. Person one is underage. That's what it's saying. Person one, you can see, person one is 13 years, so the person one is underage. That's true. And that's why it has failed. So that means if this person one comes to 18 years, then it's supposed to pass. This person one comes to 18 years. Now go test. Is that? Didn't I include 80? Let me just again see. Okay. Oh, okay. Now, what was bringing a problem was this the sentence here. I did not struck it out. I will not struck it out. So let's again do it. Let's again do it. We put 15 there. And say now go test. So it fails, and let's look what that. It says it ran two tests, and the other guy is too young, and therefore the second test failed. And so it says, assert this person one out of range. Another person, the other test was okay, and this other one failed. This other one failed. So when we make it 18, we expect that the two tests, both of them now passes. Yes, so it ran two tests and they were both successful. So they both passed. Two tests both passed. Now there's no problem from here. You can do the NAGO, the BB proofs, proof generation, proof, generation of the verification key, then verification of the proof, then you generate the solidity verifier. That will be the procedure. So let's again just do that. Again, let's just do that. Just to remind you about the code. So the code is here. That's the code I'm going to use. As we did in our earlier lesson, we need to change the name of the project. It is another lesson and another lesson. And then, so we'll be creating directory called proof inside target. You can see our target now has only two things. So we want to create this directory, and inside that directory, put the proof. That's what we've just done. Inside target, we now have a directory, and inside that directory called proof, we have inside of the proof, and that is a proof. So the next thing, as we've done after proof generation, the next thing you want to generate a key that will be used to verify that proof. You want to generate the verification key, and the code is still the same. I only need to change the name of the title of our project, and then copy the code and that command and use it here. And I'm telling it, BB write verification key, and this verification key VK should be written inside target. So you can see inside target, we now have, when we did proof generation, we formed that. And when we've done verification generation of the verification key, we formed this. This is the verification generation, the verification key. Now, after generating verification key, the next thing, as we've done, is to now use that verification key and verify the proof. So I copied the link, and you had seen the link. The link is here. BB verify. Want to verify this proof that is inside the proof directory, and we are using the verification key, and it has been verified. It has been verified successfully. From there, the next thing, as we always do, is to generate our contract, our verifier.sol, which you can deploy anytime you want on chain. So the code for that is here, and you just run it, and you get verifier.sol. You get verifier.sol. Good. Now, so later on, you may want to, instead of using these commands manually, you may want to do as we've done in our previous lessons. You may want to do it automate using scripts, build SH, key generation, and so on. You may want to automate it, and that is the best way to do it. And the other thing you may want to do, you may want now to install use JS as we used to the other time, JS, install a yarn, and so on. For the contract, you want to include a folder JS, include another folder contract, put generate proof.js, and so on, as we did in our last lesson. So we want to do that so that you generate Solidity contract. You want to do it Solidity. Now, a summary about structs and arrays and loops. Summary of our lesson. We looked at the structs, and we said structs are for grouping related data, like person and so on. Arrays are for storing fixed size collection of structs or fields. So if you're looking at 3 people, you would then say let people. But this, we said, no, it will not work. It will work in other languages. We saw how to include prover.toml in both examples that we've looked at in today's class. And we've seen how to do from Nago compile all the way up to Solidity verifier. So that is what we've looked at today. So what you need to do is once you've let me just share again. Let me share the VS Code and give you some work to do. Now, so what you can do, you can generate, you can include some folder here called circuits and move everything that is here inside that circuit. So you just say, you just come here and say make directory circuits. And it will be there. Then you move the rest, everything that is here, move it inside circuits. Just say move. And of course, when you say move, you say where it is. And then after that, we've used the move command before. After that, you'll come and generate and make a directory JS. Then include what we included inside JS in our last class. Then also make a directory contract and include everything we did last time, everything that was inside contract. Everything that was inside contract. So you do that. Then this time you will do proof generation using yarn generate, as we did in our last class. And you also do it using CLI. Just revise our last lesson and do everything we did in our last lesson. Now this, yes, once you've done this, as we've done it in today's class, just change it. Include the folders that I've just included, JS, contract, and so on. And then inside contract, include what's supposed to be included. We know what is supposed to be included inside contract, what is supposed to be included inside JS. Of course, we have Foundry and so on. Ensure that we have the Foundry.toml in the contract. Ensure that you have starter.t.sol inside test and so on. Just look at our last project and see what we had inside those folders and input them. And then generate your proof, generate your solidity verifier, and so on. So that would be a good assignment to make you understand how to write Noir contracts. That is what I wanted us to look at today. And thank you for being around in today's